Hi, this is Todd Ewing from OP-TEC, the National Center of Optics and Photonics. Today we're going to take a look at Lab 2-2, and this is looking at the beam characteristics, especially of a helium neon laser. Now you've done a similar lab in Course 1, and so let's take a look back at that lab, Lab 1-6.
We have our helium neon laser all warmed up, sitting on a lab jack, and its beam is going to be cut by a knife blade that is going to be sitting on a linear translator with a micrometer on it, so we'll be able to measure very fine adjustments to that blade position. The beam is going to be striking our photometer sensor here, and we're going to use that to measure the difference in power as we cut across the beam with the knife blade. We have our first position for our blade is exactly 15 centimeters from the output of the laser, and so we're ready to take our measurements. Since we're going to be using this micrometer to move our knife blade across the laser beam very precisely, it's important that we understand how to read this micrometer. Just to get our bearings, let's spend a few seconds and we'll see that 0 to 10 is the same as 0 to 10 millimeters. That's 1 centimeter and 10 millimeters. So each major division on the barrel is 1 millimeter. Let's crank it on down to exactly 10 millimeter and see what happens as we back out. So when everything is on 0, that would be 10.0 millimeters. This would be 10.10 millimeters, 10.20 millimeters, 10.30 millimeters, 10.40 millimeters, and now this would be 10.50 millimeters. And you'll notice on the barrel that we have passed one of the halfway marks between 10 and 11. So this is 1050, 10.60 millimeters, 1070, 10.80, 10.90, and now we are out to 11 millimeters, as we can now see the next major division after the 10 mark, we see the 11 mark. So this is 11 millimeters, and so on. So as we begin to back off in our readings, we'll be able to know how to transcribe these numbers. And so we're ready to start measuring. We're going to go the opposite direction the text suggests by moving the blade into the beam rather than out of the beam. So we are now at maximum power at 15.5 with the blade not blocking the beam at all. And 7.75 millimeters, and it looks like we pretty much have blocked the beam entirely at this point.
You'll see I have the data for the micrometer readings and the power readings for the knife blade positioned at 15 centimeters or 150 millimeters from the laser aperture. And over here we have the data for the knife blade positioned at 81 centimeters or 810 millimeters. Now for each set of measurements, let's create 2 more columns of data. So here I've added a couple of columns. You'll see I have the positions starting off at 0 millimeters, showing 0% of the power, all the way up to 2.25 millimeters, showing 100% of the power. And the same thing for the 810 millimeter set of data. What we need to do is to find the distance between the 1 over e squared positions at each side of the beam. So that would be at the 13.5% power level and at the 86.5% level. To do that, we'll have to interpret our graph of data. Let's look at a graph of our data. Here's what the measurements look like, ranging from 0 to 100% for the knife blade positioned at the 15 centimeter point and the 81 centimeter point. And what we need to do is to interpolate the curve and find the value that would correspond to the 13.5% and the 86.5%. That will enable us to determine the beam width at 15 centimeters and the beam width at 81 centimeters. Now there are several different measures of beam width that you can calculate. One of them is the 1 over e squared limits. You could also calculate the 10% and 90% limits, or the 20% and 80% limits using the knife edge. And if you have a beam profiler, then you can come up with some even more sophisticated measures of beam width. For this lab, we're just going to use the knife edge, and we'll use the 1 over e squared points on either side of the beam. Now let's return back to the data. We will have to interpolate to determine what positions would in fact have yielded 13.5% if we had stopped and measured there. And you'll see that we've got measurements that in red here that encompass the 13.5%. And so somewhere between 0.7 millimeters and 1.0 millimeter positions will be that 13.5% power level. To do that, we're going to have to interpolate. You can see that I have entered the formulas to do that interpolation for the knife edge at 150 millimeters for both the 13.5% value and the 86.5% value. And subtracting those two measurement positions gives me the beam diameter at the 1 over e squared points of 0.64 millimeters. Similarly, I can do the same thing for the data for the 810 millimeter position, and you'll see that I get a beam diameter of 1.62 millimeters. Now, if I use the formula in equation 614 to calculate divergence, I get 1.48 milliradians as the divergence for our laser beam.
So what I recommend you doing is totally blocking the laser beam out with a knife blade. And then you want to dial back and measure your power at 13.5%, your max power. And then you want to dial back until you're reading 86.5% of your maximum power. Between those 2 points are the 1 over e squared diameter. As we move along with the lab, we want to look at a couple of different ways to look at divergence. One way is to use a converging lens and to have a very small focal point. We're going to use a knife blade technique with this, but you'll find out that it's going to be very difficult to read such a small focal point. What I would suggest is introduce some of your technologies and use your beam profiler to measure your divergence. Also, what I suggest is that you replicate the knife blade experiment with using your beam profiler and then compare the data with the knife blade and the beam profiler. This will give you and your students some opportunity to talk about what differences you found and maybe consider why you have those differences. Let's take the knife blade and bring it into our beam and take a look at that on our beam profiler. This is one of the things you can talk to your students about. When we discuss this in lecture, we usually talk about cutting the beam off in nice, beautiful increments, but in reality, what we see as we introduce the knife blade, we see diffraction. And this is one example they can see in the lab, but also to give some consideration to discussion in your classroom. Another use of the beam profiler is to use this to measure beam by divergence with a lens. And I want to pinpoint where my focal point is, so I'm going to bring in my beam profiler closer and closer until I get the smallest image that I can find. You're going to find, as in the lab tells you to measure with a knife blade, that's going to be very difficult to do. Let's take advantage of the technology and let's find the size of the beam at the focal point with using our beam profiler.